Hello everybody and welcome to my 7th tutorial about Freecad CfdOF. In this tutorial I will show you how to simulate a wind turbine. We start with Freecad. First we insert a new file. We will build up the simulation with the part workbench. First we insert a regular geometrical body. The body is an ellipsoid. The first radius is 40 millimeters. The second radius is 20 millimeters. And the third radius is 20 millimeter. The U parameter is 360 degrees. And the V parameter starts with 0 degrees and ends with 90 degrees. The rotation is around the Z axis, that's okay. And the angle is 0 degrees. So we can say construct, and our hub is already there. We close. Then we need a cylinder. We click on cylinder and we added the parameters. The radius is 5 millimeters. The height is 40 millimeters. The angle is 360 degrees. The position is 0, 0, 10 millimeters. And we are going to rotate this around the Y axis. So here is 1, here is 0. And the rotation angle will be 90 degrees. Okay. So we click on OK. Now we must go to the draft workbench. And we want to build a polar array with this cylinder. So the middle point is 0, 0, 0. And the number of elements is 3. And we click on OK. Now we go back to the part workbench and we insert a cube. We added the parameters of the cube. The length is 0.1 meter. The width is 50 millimeters. And the height is 2 millimeters. And now we have to change the position. In X direction, it is 40 millimeters. In Y direction, it is minus 22.615 millimeters. And in Z direction, it is minus 4.232 millimeters. I've calculated these values before. They come out of sinus and cosinus. The reason is that we will now apply an angle of 30 degrees, and we will rotate this cube around the x-axis, and the rotation angle is 30 degrees. We click on OK, and we go back to the draft workbench and go also to the polar pattern. The number of arrays will be 3. The point of rotation is 0, 0, 0. And we click on OK. So now we have something that looks quite similar to a wind turbine, of course, this is very small. The diameter is, yeah, diameter is not what you expected. Normally, a wind turbine has a diameter of 20 meters or 50 meters or even larger. So we make only a very small wind turbine, and of course, what we are building now, this is not very optimated. But the only reason why I chose this is that this is very easy to design. So that was the reason why I chose this. We go back to the part workbench. And now we mark the ellipsoid, the array, and the second array. We must make a cut. Cut is only possible if we make a compound. So now we have our compound. This is needed because we for the simulation we need the negative space. So we go again back to the file, insert a cube, and edit the cube. So the size is 0.4 meters. The width also 0.4 meters. And the length is 1 meter. And we must also adapt the position. The position is minus 0.2 meters in x direction, minus 0.2 meters in y direction, and minus 0.7 meter in z direction. Okay, now our rotor has disappeared because the cube is covering all that's intended like this. We can mark the cube and the compound and say that we want, notice, yes. So we can make a cut. And yes, cut is not very good to find, so we remove cut. So we rename this to cut rotor. This will be for mesh definition and so on. This is easier to find. So we want to look inside, so we click on the right button of the mouse. Yes, here it is. And we can change the transparency. So here you see that inside we have the rotor. So this is okay. We can close. Furthermore, we need a second tube for the refinement of the mesh. So we insert a cube and click on this cube and define the measurements. So the length is 0.5 meters. The width is also 0.5 meters. The height is 0.2 meters. And the position is minus 0.25 meters. And here also minus 0.25 meters. And in Z direction, it is minus 0.1 meter. Okay, so this cube is covering the rotor. We will use this afterwards for refinement. So now our model is complete and we can go to the CFD workbench. We will insert an analysis container. The physics model steady, single phase, incompressible, that's okay. And it is a viscous medium, and we will approximate the turbulence with a Reynolds averaged numerical simulation with RANS. Okay? Fluid properties, it's air, that's okay. The initializing will be potential flow, and this one also potential flow. So now we have to define the boundary conditions. We pick this phase and define this phase as an inlet. So we go on the boundary conditions, say this is an inlet. The subtype is uniform velocity. The flow is running in negative z direction, so we define this as minus 20 meter per second. We click on OK. Now we click on, on the left face. This boundary will be open, but also the top layer, the top face, and the right face. Okay. Okay, we click on the opposite side of the inlet. And this, of course, will be the outlet. We click on OK. Now we must define the face on the lower face. So we click here. And this will be wall, no slip, that's OK. And we click on OK. But this we will rename to ground. So label will be ground. And now we must define the boundary conditions for the rotor itself. We click on the boundary conditions. And the boundary is a wall. The subtype will be rotating, but rotating is not available, so we say translating. We insert a dummy value of 10 meter per second. And now we must click these surfaces. It's very difficult to click on them, so it's easier to say select from list. The object is a cut rotor. Now you see the reason why we renamed this. So we can say select all. So just for information, the first 6 faces are the outer faces. So you can click on them and you see where they are. So I say select all, but we don't want the outer faces to be selected as well. So we deselect them. So I say done. And now our boundary condition is complete. We click on OK. And we rename this label as well. We call this rotor. We have also a cube for the refinement. It makes sense to rename the label from Würfel 002 to refinement. So we go again to the cut of the rotor. And here we can define the mesh. The measure we will use is CF mesh. And the base element size is 20 millimeters. So we click on OK. And now we must define the refinement. We go on the definition of the refinement. The relative element size is 0.5. we will define this via an internal volume. The reference we will select from the list. This is the refinement. And we click on Done. Now our first refinement is complete. We make it, we mark the cut mesh a second time, and we define our second refinement. So this time we will define this via the surface. The relative element size is 0.25. The refinement thickness is 10 millimeter. And the reference, in this case, we will define this also via the list. We go to Cut Rotor, select all faces, and deselect the first 6 faces. We can click on Done. We click OK. And now our mesh definition is complete. We go again to the Cut Mesh, make a double click, write the case, and let the mesher run. Now meshing is complete. We can review the mesh. So we say load surface mesh. Okay, in that case, you don't see really much because, yes, we see the refinement of the mesh, but we cannot see inside. In this case, it would make sense to make a cut in Freecad, or we can go to Paraview and make the cut in Paraview. I say close. And now it's time to start the simulation. We go to the CFD solver, make a double click on it, and we write the case. So now we have to edit the file because we must say that we have a rotation. So we go to Edit. We go to the directory 0. We edit the file U. And here we have the boundary condition for the rotor. The type is a rotating wall velocity. So here we need, you must define the origin. The origin is 0, 0, 0. We must define the axis. We will rotate around the z-axis, so we have 0, 0, 1. And we must specify the speed. So the speed will be 100. So 100 is similar to 954 revolutions per minute. So now we are complete. We can say save and close the file. We go back to case, we go to system and edit the directory control dict. We must insert the commands for the force evaluation. We take the commands out of the tutorial from CSIR. It's just copy and paste. We go to the editor and paste it. The patches is rotor. The density is 1.2, that's the density of the air, that's okay. And the center of rotation is 0, that's also okay. So we save this, close, go back to Freecad and start running. The simulation has finished after 800 iterations. The time was 34 minutes. Now the simulation has finished. We can review the results with Paraview. We click on Paraview. So taking a view on Paraview, that's you only see the outside, so you don't see much, but we go to the last time step. So we can take a look on the velocity outside in Z direction, because this was our boundary conditions. We see that here we have a velocity of minus 20 meter per second. That was our boundary condition. That's okay. To look inside, we can slice. So first we slice in the Z direction. We slice at 0, 0, 0, and then take a look on what's happening. So here we see that we have already, so that we here have a different pressure distribution over the wings of the wind turbine, and we can take a look on the velocity. So Z direction, we see that all around we have the boundary condition of minus 20, but in the area of the wings we have a velocity going in direction into the inlet, so in an inverted direction. We can take a look on the X. So here we have a plus, here we have a minus. We can take in epsilon direction the velocity. So here we have minus, here we have a plus. So in the next analysis, we will take a look on the steam tracer. We will start all points. We will start with 0.3, and we will start from minus, in epsilon we will start from minus 0.2 up to plus 0.2, and the same in x direction, minus 0.2 and plus 0.2. We will reduce the resolution. We will go to 200 and start apply. So what we see now is that we that on the start the steam or the flow is going straight. We can reduce the resolution to 100. Yes, now we can see more clearly. We can see that the flow is going straight from plus Z up to minus Z, and in the area where the rotor is, we get some kind of rotation, so we can close. And the last analysis will be the glyphs. We click on the glyphs. We will reduce the number of sample points up to 1000, and for the velocity we will use the velocity out of the cells. So we click on apply. Yeah. So what we see is that we have a velocity mostly into in the Z direction, and in the area of the rotor, we get some kind of rotation which is intended and which is the use of the rotor. Okay, we remove the glyphs, and in the next step we will also analyze the velocity. So we say plot over line. So the start is -7 and +3, that's okay. But here we will go to 0.1 and also 0.1. And here we also will use 0.1 for the x-coordinate for both points, 0.1. Okay, now you can see the line, and we click on apply. We are not interested in omega and the parameters for turbulence. So concerning the pressure, we see some move this, and the velocity. So we see that that in the area of the rotor we have some change in the velocity. So we can close Paraview, and we can take a look on the torque. We go to the directory post-processing, forces all, 0, moment, edit, and the torque is given as a last time step. So here you see that we are mostly interested in the values in Z direction. So this is the resulting torque. This is 0.29, and this comes mostly out of the pressure, and there is some negative impact due to the viscosity, due to slip effects over the surface. I repeated this simulation several times with different parameters. So the result is given as a blue line. If the speed increases, the torque will become lower. The orange line is the resulting power. So you see that an optimum speed would be around 11,000 revolutions per minute. But it's important to say that this is only valid for one input speed, for the input speed of 20 meters per second, and only for one tilt angle. Normally the wind turbines can change the tilt angle. We've calculated this with 30 degrees, so in real life it would be necessary to calculate this also with other tilt angles and with different inlet speeds, so it takes a lot of time to calculate it. As far as I know, it's currently not possible to calculate this with a sweep or with a ramp function. The current version of OpenFOAM would be able, but this version is not implemented. As far as I know, the version that's implemented in Freecad is a version from 2012, and there a ramp is not possible. So thank you very much for your attention, and I hope to see you in the next tutorial. Bye bye.